Okay, we are looking at section 3.4. Everyone has a gift. Section 3.4 is on solving exponential and logarithmic equations. And we're just going to go over some of these examples, and I'm going to put you into groups to kind of finish up this gift. For number one, we're solving 2 to the x equals 15. Since we cannot get 2 and 15 to both have the same base, we cannot use the one-to-one property here, but we can take this, which is in exponential form, and rewrite it in log form. So how would we do that? What would that look like, Brianna? All right, so we solved for x. This would be our exact answer, but we probably also want a decimal approximation. So grab your calculator, do log to the base 2 of 15. Once again, if you had a TI-83 or TI-84, you could not do this directly. You would have to use the change of base formula that we talked about last class. But you guys have the Inspire, so you can do log to the base 2 of 15, which means 2 raised to what power gives me 15? And your answer is? So x is approximately 3.907. Everybody okay with this? All right, let's take a look at number 2. ln of x minus ln of 5 equals 0. My suggestion on this problem would be to just add ln of 5 to both sides. So we get ln of x equals ln of 5. At this point, we can use the one-to-one property. If ln of x equals ln of 5, that means that we're taking log to the same base of each side, so x would have to equal 5. Are we okay with this? Yes. All right, let's take a look at number 3. Number 3, 1/5 to the x power equals 125. This time we really could use the one-to-one property, so we could get both sides to have what base? Bailey? 5, sure. So 1/5 could be written as 5 raised to what power? One-fifth is the same as 5 raised to the -1 power. So I've got 5 to the -1 equaling, and 125 would be 5 to the third. Oops, I forgot something. So this is 5 to the -1 has to be raised to the x, right? Equals 5 to the third. So if I'm multiplying, raising a power to a power, I need to multiply, so I'd get -1x as the exponent here, 3 here. Our bases are the same, so that means that -1x must be equal to 3, and so we get x equals -3. Are we okay with this? All right, let's take a look at number 4. e to the x equals 13. Again, if we are trying to solve for an unknown that's locked up in an exponent like this, we're trying to solve for x. If it's locked up in the exponent, we're going to rewrite it in log form. So what's that going to look like, Sydney?
That's going to be log to the base e.
All right, log to the base e of 13 equals x, which is the same thing as saying ln of 13 equals x. Again, this is our exact answer, but if we want a decimal approximation answer, what would that be?
2.5.
Decimal approximation, x is approximately 2.56. Are we okay with this?
Yes.
All right, let's take a look at the next one. Number 5, ln of x equals -8. To solve this one, Paul? All right, let me catch up to you. So you're thinking of ln of x is log to the base e of x equals -8, and did you rewrite that in exponential form? And what's it look like? All right, so we went from log form to exponential form, and now we can use our calculator, because this would be our exact answer. But if we want a decimal approximation, x is approximately what? 0.0003 3.5? Are we okay with this? All right, let's take a look at the next one, number 6, log x equals -2. How would we go about solving that one, Jessica? Do people agree with that? Remember, if we don't see a base, it's understood to be a base 10, so Jessica's going from log form to exponential form, so we can solve this. And 10 to the -2 is the same as 1 over 10 to the +2, so do we get 1 over 100 as our answer?
Do you want that as a decimal or a fraction?
I prefer fractions if they're exact, so I think that would be a good answer. All right, let's take a look at number 7. For number 7, it says we're solving each equation and approximate the result to 3 decimal places if necessary.
Can't we just do -x squared equals,
All right, again, that's using the one-to-one property that our bases are the same. That means the exponents need to be the same. So we get -x squared equals 5x plus 6. So I would add x squared to both sides. Does that factor?
yeah, x plus 3, x plus 2.
X plus 3, x plus 2. Again, zero product property. I got two things being multiplied together to give me 0. One of them has to equal 0. So I get x equals -3 or x equals -2. You should check them both, make sure that they work in the original equation. Let's move on to number 8. For number 8, what would you do first to solve for x in this problem? Lindsay? So multiply the 3 and the 4 and get like 12 raised to the x? Do people agree with that? Well, all right, but who said PEMDAS? All right, so PEMDAS. So we got to do, please excuse my dear Aunt Sally, parentheses, then exponents have to be done before multiplication. So unfortunately, we cannot do that. So Lindsay, what else could we do instead? Sure, let's divide both sides by 4 first. So we're going to get 3 to the x equaling 16. And then what would we do to rewrite that in exponential? No, it's already in exponential form. Louis, how would we rewrite this in log form so we can solve for the log to the base 3 of 16 equals x. So that would be our exact answer. What's our decimal approximation to 3 decimal places? X would be 2.524. Are we okay with this? All right, let's take a look at, I'm going to leave you with number 9. You'll be able to do that one, I think. Let's take a, would I skip number 11 or number 10? Where's number 10? Number 10, I think you're going to be okay with that one if you're careful with your order of operations. So I'm going to skip over to number 11. Let's take a look at number 11. For number 11, notice we've got e to the 2x minus 7e to the x plus 12. My suggestion for you on this problem is if you let, for example, w equal e to the x. If w equals e to the x, then e to the 2x would be equal to what? Is it w squared? Because wouldn't this be e to the x raised to the second? Same thing, right? And so that would be equal to w squared. So I can rewrite this as w squared minus 7w plus 12 equals 0. Right? And go ahead and solve that. You're going to factor if you can and set them equal to 0. And don't forget you got to plug it back in, right, to get your answer in terms of x. So I'm going to put a little dot, dot, dot on that one. And I'm going to have you finish that one up in groups in just a little bit. Meanwhile, I think you can do number 12 with no problem. Let's talk about, I think you can do 13 with no problem, I hope. Let's talk about number 14 for a minute. So stop what you're doing on number 11 or whatever you're working on. Let's take a look at number 14 together. If we're trying to solve this, can we use one of the properties that we learned last class to help us rewrite the left side of this equation? Can I rewrite this quotient rule? Can I rewrite that left side as just one logarithm instead of two separate logarithms? So what's this going to look like? Hands, please. Louis.
Base 3, 5x plus 13.
Equals log to the base 3 of 3x. Do people agree?
Okay.
Now can I use the one-to-one property? All right, so I'm going to let you finish this. Patrick, got to wake up there. All right. Okay, so I'm going to let you finish that one up. I think you're going to be okay with number 15, I hope. And number 16, I think you're going to be okay with that. Number 17, I'm just going to say similar to number, which the one we just did, 14? Right? Yes. Yes, it is. Hang on a second. Whoops. When we solve this equation, when you set this up, is just going to be linear. True? 5x plus 13 over 6 equals 3x.
5 by 6.
Good idea. So we're going to
5x plus 13 equals 18x. 13x equals 13x.
Okay, so here's my point. This x turned out to equal 1. What if it had turned out to equal negative 1? Are we still going to accept that as our answer? Why not? You can't have a log of a negative number, so if I tried to check it and I plugged in negative 1 here, I'd have log to the base 3 of negative 3. What's log to the base 3 of negative 3? Undefined, does not exist. We didn't go over that non-calculator part of the quiz, but please make sure you understand how to get all those answers on there. All right, so in other words, x equals 1 is good because it's greater than 0, right? But if it was less than 0, that would be a problem. So I think why am I pointing that out? Because on this problem, this one, when you use a property of logarithms that we talked about yesterday, you may end up with a quadratic, right? Because you're going to have x times x minus 9. So just be on the lookout for what's in the domain, plug them back in and check them, right? It's very important to check for extraneous solutions. All right, quadratic, check for extraneous solutions. Are we okay with this? Okay, and number 18. You have deposited $1,000 in an account that pays 6.25% interest, compounded continuously. How long will it take your money to double? All right, we're going to want to use the PERT formula because it says compounding continuously. All right, and what are we plugging in for what?
1,000 for P.
1,000 for P. E is a real number. It's 2.718 approximately. All right, and the years? We don't know. So we're going to X or T or whatever you'd like. What about the A? Why 2,000, Billy?
2,000 plus 1.
We want it to double. All right, so we're going to plug in 2,000 here. And what would we do first to solve this? Patrick? Divide by 1,000, I heard you say. So we get 2 equals e to the 0.0625 t. And then what would be our next step here, Paul?
So that equals
Log to the base e of 2 equals. Everybody okay with this? So Paul went from exponential form here 2 logarithmic form. And now this is really, sure, it's ln of 2 equals 0.0625t. And our last step would be to, all right, so t is approximately what? 11.1. So it's going to take you a little bit more than 11 years to double your money if your bank is paying you 6.25% interest compounded continuously. Questions on this? All right, was there another one?
Yeah.
All right, last one. The number y of endangered animal species on a protected wildlife preserve from 1990 to 2004 can be modeled by y equals negative 117 plus 159 times ln of t. T can only go from 10 to 24, where t represents the year, with t equals 10 corresponding to 1990. During which year did the number of endangered animal species reach 342? All right, we plug in 342 for y. So if 342 equals negative 117 plus 159 ln of t, and then you're going to solve this the rest of the way. I'm just going to put a dot, dot, dot on this. By the way, what are we talking about here? We're talking about an algebraic way of solving, but you could also do a graphical way where you type this function into your calculator on a graphs page, right? And you can look at the graph, you could analyze the graph, you could pull up a table, control T, and so on. Are we okay with this? All right, so at this point, I am going to put you into groups. I'm going to let you work, I'd say just until 10:30 on this, so getting as many of these done that we skipped over as you can. Hopefully you can get them all done by 10:30, and then we're going to regroup and talk a little bit about section 3.5.